Hello and welcome to this video on identifying whether a value and vector that are given are an eigenpair of a matrix. So when I say eigenpair, I mean that this particular value and vector that are given are an eigenvalue and corresponding eigenvector of a given matrix. All these things will be defined in the beginning of this video. Alright, so it's going to start off, I'm going to identify what it means for a vector to be an eigenvector of a given square matrix, what it means for a value to be an eigenvalue of a matrix corresponding to a given eigenvector, and then those two together make up an eigenpair, right, which is in the title of the video. Then I'll talk about how, what does it mean for us to have eigenvalues and eigenvectors of a matrix in terms of transformations of one vector into another vector in Euclidean space, and I'll just be looking at basically R2 and R3 here so we can actually picture the transformations. Anything with higher dimensions be really tough to picture. Then finally, I'll just go over a couple examples in which I'm given a value, I'm given a vector and a matrix, some square matrix, and I'm asked, the title of the video, are this value and vector an eigenpair of that matrix? All right. So here I'm talking about defining eigenvalues and eigenvectors of matrices. Right. So number one, a non-zero vector, non-zero vector, say x, which is in Rn, so R2, R3, R4, some Euclidean space, is an eigenvector of an n by n, square matrix A if a scalar called lambda, this is the Greek letter lambda here, little wavy, little stick holding up a wave, or a little guy with his head drooping and two legs, I don't know, however you want to think about that. It's called lambda, Lambda. A non-zero vector from Euclidean space is an eigenvector of a square matrix A if a scalar called lambda exists such that A times x is equivalent to lambda times x. So the matrix times the vector is equal to just the scalar times that same vector. In other words, a vector is transformed into a scalar multiple of itself. Because remember every matrix corresponds to some linear transformation, right? So if A was the standard matrix, of some linear transformation from from Rn to Rn, then the transformation would take x, this special eigenvector. An eigenvector gets mapped to a scalar multiple of itself, or an eigenvector is transformed into a scalar multiple of itself, and I have that written on the next page as well. Alright, so again, this is a number here, lambda. It's called the eigenvalue of A, corresponding to eigenvector x, a vector x on both sides. Alright, and as I mentioned, this value lambda is an eigenvalue, An eigenvalue of A is a scalar multiple lambda that corresponds to the eigenvector x, So just in this if this is a true statement, if I can find, I'm given a matrix A, if I can find a vector x and a value lambda that make this true, then x is an eigenvector and lambda is an eigenvalue corresponding to the eigenvector x. And finally, on the definition side, an eigenpair is simply an ordered pair you'll see in some texts written where you have in parentheses, the first position, the eigenvalue lambda, comma, and then in the second position the vector x, the eigenvector x that it corresponds to. Right? These are the lambda and x that make this statement true. It's an ordered pair of an eigenvalue and the corresponding eigenvector. Right, it's as simple as that. Alright. So as I mentioned, remember whenever you see a matrix, you can think of that matrix as being the standard matrix for some linear transformation. So if I have an n by n matrix, we basically have a standard matrix for a linear transformation between the two Rn and Rn, right? N-dimensional Euclidean space. So like I was saying, multiplying a square matrix by a vector transforms, right? We're talking about linear transformations here. Transforms the vector into another vector, right? Into its image under that transformation. So say, for example, I have a matrix A. Again, we're only dealing with square matrices now, right? In whatever chapter on eigenvectors and eigenvalues you're working with, you're dealing with square matrices only. I have a 2 by 2 matrix here with columns 1, 1, and -2, 4. Again, this could represent some, be the standard matrix for some linear transformation from R2 to R2. And suppose I have my input vector v, or again you can call it x, I'm calling it v, whatever. Right? I have a vector v from R2, say the vector -2, -1, and then I apply the transformation, right? Meaning I multiply it by this matrix, and in multiplying these two matrices, right, I get the output vector, a new vector, right, another vector from R2. And if you were to multiply this, 2 by 2 times a 2 by 1, you get this 2 by 1. The output vector from R2 is 0, -6. Now, in this example I've just shown here, my vector -2, -1 was transformed into the vector 0, -6 by this matrix. Right? Or you could say, under the transformation defined by this matrix. Same meaning. These two vectors, though, do not point in the same direction, right? The reason I'm going to be working strictly with R2 and R3 in this video, so I can actually show you some pictures of vectors. All right, so let me go to this is the website GeoGebra.org, right? And it's a nice website with a nice calculator, a graphing calculator on it, and you can put in vectors and stuff. So I've got the origin marked off, and here's that vector I mentioned. Vector, let me zoom in a tad there. Maybe see it in a little light green. I could change the color, I guess, but there's vector v1, this -2, -1, right? Left 2, down 1, and applying the matrix to this, right? When I multiplied this by matrix A, I got the vector 0, -6. Now you can see that 0, -6, again this light blue here, definitely does not point in the same direction as v1, right? So this vector here, -2, -1, under the transformation with standard matrix A, or multiplying the A by this, transforms me into this vector here, right? 0, -6. Just a vector pointing down 6 units from the origin. Clearly not pointing in the same direction, right? So what we would say here is that v1 is not an eigenvector, right? Because when I multiplied that matrix by v1, I got another vector, I got an output vector that wasn't a scalar multiple of v1, right? And remember, scalar multiples of vectors will point in the same direction or the opposite direction. They'll like form a line. If you looked at all the scalar multiples of v1, they would form a line containing vector v1 here in the same direction and opposite direction as v1. And you see that v2 here is 0, -6 clearly does not do that. All right. So back to my page here. So like I was saying, this new vector, this output vector 0, -6, this is not a scalar multiple of my my input vector, the vector I applied the matrix to or multiplied the matrix by, of -2, -1. Okay, so what that tells me is that the vector -2, -1 is not an eigenvector of this matrix, right? An eigenvector of matrix A. Right, and that's big. Right? That's the whole point of this video. We're trying to figure this out. Given a vector, is that vector an eigenvector of a certain matrix? All right. Well, let's say sticking with the same matrix, right? So the same matrix A with columns 1, 1, -2, 4, the same 2 by 2 matrix. As I mentioned on the GeoGebra page, eigenvectors are special. Eigenvectors of a matrix A are transformed into scalar multiples of themselves. Right? And that's what this whole equation is saying, right? Back on the first page. Right? It's eigenvectors satisfy this equation here, where if I took the matrix multiplied by that vector, the output is simply a scalar multiple of that same vector. So for instance, taking the same matrix A, and now this time my vector v is, instead of -2, -1, now the vector I'm looking at is -1, 1 from R2. I apply matrix A, I multiply by matrix A, so I take this matrix A that we had, multiply by -1, 1, 2 by 2 times 2 by 1, gives me an output vector, right? My input being -1, 1. The output, what it's transformed into or mapped to is the vector -3, 3. Well, do you see that this vector -3, 3 is simply 3 multiplied by the original input vector -1, 1. So -1, 1 under this matrix, right, when I multiply by this matrix, is mapped to or transformed into a scalar multiple of itself, just 3 times itself for the output. All right, so I'm seeing this here. A times V in this case is equal to 3 times V. Right, so this is true, and this means that V, all right, I can say the following 3 things about this particular example. Oh, and let me show you the picture as well. All right, I'll go back to the GeoGebra site. All right, so here's the vector -1, 1 in R2, right? Just left 1, up 1, that direction. Multiplying by matrix A transformed it into this vector, -3, 3, and you see that that vector is pointing in the same direction. Right? They're on the same line. Okay, and that's what an eigenvector does under some matrix A. A times that vector will just simply be a scalar multiple of that vector. Right? And the scalar that you're multiplying by, which in this case is 3, that would be called the eigenvalue of the matrix corresponding to that eigenvector. All right. So I have all that written here. So for this particular example, right here, we could say the following. So for this example, we would say that this vector, -1, 1, is an eigenvector of A, right? Because A times this vector gives me an output that is simply a scalar multiple of this vector. And then that scalar that multiplies by the input vector, that scalar multiple, the scalar was 3. That's our lambda in this case, right? These eigenvalues. So lambda equals 3, they would say, is the eigenvalue of A corresponding to eigenvector -1, 1. And when I say this, that means if I multiply A by this vector, I'm going to get 3 times that vector as an output, as a result. And then putting these together, we get an eigenpair of matrix A. You know, and again, the first in these eigenpairs, the first component is simply the eigenvalue, and it's corresponding to the the eigenvector is the second component. So this ordered pair with 3 comma and then the vector -1, 1 is an eigenpair of A. And again, if you're seeing this, all this means is that the matrix A times this vector would give me an output that's 3 times that vector. The output would be the scalar multiple of that vector. That's 3 times it. And it's really that simple, right? If we're asked if a certain pair of value and vector are an eigenpair of a matrix, you just multiply the matrix by that vector, and do you get a scalar multiple? Do you get that scalar multiple of that vector as an output? So I've just got a couple examples, right? And this isn't going to be terribly long today. I think it's a pretty simple concept. Alright, so here, my matrix, so I'm asked in the following, I only have 2 examples because every single one I'm doing the same stuff. Determine if some pair of number comma vector lambda comma x is this pair an actual eigenpair of the given matrix A. Right? So matrix A here is a 2 by 2. All right, so with columns 2, 3, 4, 13, and what I'm checking, is this an eigenpair of A? Could I replace lambda with 14 and the vector with 1, 3? Right. So the big question I'm trying to answer here is this: is A times x equal to lambda times x? Right. If the answer is yes, great. This is an eigenpair. You would call 1, 3 an eigenvector, and 14 an eigenvalue of the matrix A corresponding to 1, 3. And then this an eigenpair, as I said. So let's check it. Now again, don't start with this. Right? I don't know that this is true, so I can't write that these are equal. I'm trying to show that these are equal. So you could do this a couple ways. I could just start with the left side. All right, let's look at the left side of that equation. What's A times vector x? So I got the matrix A, right, this 2, 3, 4, 13 matrix, multiplied by vector x, right, the vector given to me is this vector 1, 3. And let's see what we get. This is a 2 by 2 times a 2 by 1, so I'll get a 2 by 1. And first row, first column, I'd have 2 times 1. Just remember how matrix multiplication works. I'm hoping you do, right? You've probably seen it a bunch by this point, I'm assuming. 2 times 1 is 2, 4 times 3 is 12, 2 plus 12 is 14. And then for the second row, first column, 3 times 1, 3, 3 times 13 is 39, 39 plus 3 is 42. And then you could then work with the right side of the equation if you want. But I do see right here, the big question is this matrix times this vector going to be equal to 14, right? Lambda is 14 here. Is the matrix times the vector equal to 14 times the vector? Well, let's see what happens if I pull a 14 out of this vector here. If I pull out the scalar of 14, well, first component is 14 times 1, and then the second component is 14 times 3, right? 14 times 3 is 42, and look at that. The answer is yes, right? This is the left side, this is the right side of the equation here, and we are seeing that they are indeed equal. All right. So the matrix times the vector is equal to that value times the vector. So yes, right, the answer is yes. Now you could have worked with these separately, said a times x equals the vector 14, 42, and then started with done the right side down here and said, all right, what's lambda times x? All right, said what's lambda times x? So that's 14 times 1, 3, and then put this in and say, hey, that's 14, 42, and they're the same. Oh my gosh, they are equal, right? So either way, the answer to that question is yes, right? So what we could state here are the following. You could say the following three things about this particular example. All right. So because that ended up being true, we can say we could say that the vector 1, 3, all right, is an eigenvector of A. Now notice I say an eigenvector because you're going to see there's usually more than one eigenvector of a matrix, a square matrix. All right, so the vector 1, 3 is an eigenvector of A. Another thing we could say here is that the value 14 is an eigenvalue. Well, it's the only one corresponding to this vector, so I'll say is the eigenvalue of A that corresponds to the vector 1, 3. Now, A can have more eigenvalues, corresponding to different eigenvectors, but for this particular vector, the output's only going to be 14 times it, right? The only one that I get. So is the eigenvalue of A corresponding to eigenvector 1, 3. And the last thing I could say involving this, or we could say that this pair with 14 and then the comma, then the vector 1, 3, this is an eigenpair, of A, right, of matrix A. All right, so I mean that's what was being asked of us, that last part, right? But all three of these things could be said about this matrix and this value in this vector, right? That the vector is an eigenvector of the matrix, the value is an eigenvalue of the matrix corresponding to that vector, and the two together make an eigenpair of the matrix. Okay. And then again, if you want to look at a picture of this, right, these are all vectors in R2. Back to GeoGebra here, right? This was the vector 1, 3, right? That was my my input vector. I was checking to see if that was an eigenvector. And then the output ended up being the vector 14, 42. All right, and you can see that they point in the same direction. Right, I know they're both black, but you see how they're on the same line together? They're pointing in the same direction. That just means they're scalar multiples of one another. All right, the output, when I take 1, 3, multiply this matrix by 1, 3, the output is simply a scalar multiple of 1, 3. So that means 1, 3 is one of these eigenvectors, right? Only the eigenvectors do that under a matrix. Right? Okay, so I've just got one more example here. Like I said, this is a pretty simple process, pretty simple procedure. So again, here's another one. So suppose I'm given a square, another square matrix, but this time, I'm dealing with a 3 by 3 matrix. So my input vectors will be, vectors from R3, and the outputs will be vectors from R3, or three-dimensional Euclidean space. And the question again is the value of 9 and the vector x of 2, 7, -1, does this form an eigenpair of this matrix, right? So is that an eigenvector of this matrix, and is 9 the eigenvalue of this matrix corresponding to this vector? Well, let's see. Again, the big question here is A times the vector, is the matrix times the vector going to be equal to the number lambda times the vector? So again, you don't write this. Don't say these are equal right now. You don't know that they're equal. You're trying to show that they're equal, or not. So again, I'll work with the left side first. The left side of that statement. What is A times the vector? So that's this. I'll write the 3 by 3 matrix again. 2, -1, 4. 2, 0, 0. 0, 1, -1, multiplied by the given vector here in this pair is 2, 7, -1. Alright, so it's like my input is like a vector from R3 here, and then the output will be another vector from R3, right? Some of 3 components. A 3 by 3 times a 3 by 1 will give me a 3 by 1. First row, first column, I'll end up with 2 times 2 is 4. 2 times 7 is 14, and then plus 0. So 4 plus 14, 18. Okay. Then the second row, first column, -1 times 2 is -2, then you have 0, then you have -7. -2 plus -7 would be -9. And right away, I'm seeing that these are not going to be equal, because you see the vector I started with, 2 times 9 is 18, but what's 7 times 9? 63. This is not 63, right? And remember, in order for a vector to be an eigenvector, the output needs to be a scalar multiple of that input vector. So I'm already not seeing that here. But then finally, the third row, first column, I'd have 8 plus 0 plus 1, that's 9. And again, I mean, I can multiply the first component by 9, but then the second component by -9/7, and then the third component by -9. I'd have to. There's not a single scalar to multiply by this vector here to get me that one. All right, but let's finish it. All right, let's look at the right side of the statement. The lambda times the vector, the scalar times the vector. Now the scalar given here is 9. 9 times the vector x, and the vector was 2, 7, -1. Right? And in multiplying these, this vector by this scalar, just multiply each component by 9. That's 18, 63, and -9. Right? Which these are not equal. These are not equal. Right? And that's a problem. So the answer to my question is no. All right, no. So what we're seeing here is that one, the vector 2, 7, -1 is not an eigenvector. It is not an eigenvector of this matrix. And if it's not an eigenvector, then you don't even need to talk about eigenvalues. Right? Because the only way you're going to have eigenvalues is if your vector is an eigenvector, right? If its output is a scalar multiple of itself when you multiply by the matrix. So the only other thing I could really say then is that this pair that I was given is not an eigenpair of matrix A. So 9, and then the comma, the vector 2, 7, negative 1 here that I was given is not an eigenpair of matrix A. Right. And let's look at this geometrically. Look at a picture of this in R3, three-dimensional space. So I'm going to go to GeoGebra. Now GeoGebra does have, this is the 2D calculator that I have up, but they also have a 3D one. All right, and here's vector 2, 7, negative 1. Now that's pointing below the xy plane there. See, it's pointing below the xy plane. Kind of go around here. You can see this vector, the light green vector, that arrow there pointing from the origin. Okay, so I go back to the main screen. So it's dotted because it's below the plane there. Then when we multiplied this vector, by matrix A, we got this other vector with components, and when I multiplied by matrix A, I got components 18, then negative 9, and 9. Right. And look, clearly, these two vectors are not on the same line. They're not scalar multiples, right? Because again, if they were scalar multiples, they would be pointing in the same direction or opposite directions, but on the same line. And you can very clearly see that the green vector and black vector are not pointing in the same direction or on the same line at all, right? So we can say we can see now right away that this green vector, the vector 2, 7, negative 1 that I had, is not an eigenvector of that 3x3 matrix we were given. Right, because the matrix times the vector was some vector that wasn't a scalar multiple of 2, 7, negative 1. This vector 18, negative 9, 9, as you saw in the picture, does not point along the same line as 2, 7, negative 1 does. Okay. All right, and it's really that simple. This objective here, identifying if a given value and a given vector are an eigenpair of a matrix. Just multiply the matrix by the vector, and do you get as an output that scalar times that vector again, right? That scalar multiple of that vector. It's very simple, very quick, and I think probably one of the easiest things I've shown in my most recent videos. All right, so hope you enjoy practicing stuff like this, and thank you for watching.